Welcome everybody to the STEM Education Institute seminar for today, Tuesday. We are delighted to have Steve Bennoun with us. Dr. Bennoun is a lecturer at the Department of Psychology at UCLA. He did his bachelor's and master's in mathematics at EPFL Lausanne, so École Polytechnique Fédérale de Lausanne, and then got his PhD in mathematics at the University of British Columbia, after which he went to Cornell and was an active learning lecturer there in the Department of Mathematics, following which he moved to UCLA. He's going to tell us today about a new course that they've designed at UCLA. So the title of the talk is Transforming Calculus for Life Sciences by Teaching Dynamical Systems and Bifurcation Theory. So I'm looking forward to hearing this. Steve, the floor is yours. Welcome.
Oh, thanks a lot. Good afternoon, everyone. So today I'm going to talk about this new course, calculus course that has been developed at UCLA for quite a few years now, and where the idea was really to completely transform what was a calculus for life sciences, where you have it was really a calculus course and then a few connections to a few applications in the life sciences, most of them relatively superficial, to a course where we really have the biology and life sciences motivating the study of mathematics. So let me share my screen. Okay. So how did all this started? Well, I'm first going to talk quickly about the origin of the course, why it was developed, how it started, and then I'll talk about the course itself. That will be really the main part of this talk, what we do in this course. I talk then quickly about outcomes, and then how it's been implemented at Cornell, what was before, and where we actually used the textbook from the course to adapt it. And so this last part is really about how can that be done in another institution. Okay, so how did everything start? Well, at the beginning, there was really this need that came out in 2012 from the Division of Life Sciences at UCLA, where they had some needs and some wishes from the math course that the students in the life sciences were taking. So they were taking sort of a traditional calculus for life sciences course. And the problem was the one that I mentioned before, namely that they wanted to have like really true and deep connections between the math and the biology. Have also some math, have the students learn some math that's actually used in the life sciences research. And not necessarily learned about limits and compute derivative by hand, but on the contrary, concepts that would be really used right away in upper division courses. And then there was one last concern, which was the equity gap, and also in general, the perception of the course by the students that was pretty negative. For instance, in terms of confidence in their math ability. Students after taking that calculus course would see their confidence in doing math decrease. Another reason to start and to completely redesign this course was several calls that had been made by professional societies to change mathematics for life science students. So one of them was from the Howard Hughes Medical Institute and the American Association of Medical Colleges, where in their report, Scientific Foundations for Future Physicians, they list what they call undergraduate competencies. So some abilities and skills that the undergrads should develop, what they want to see in their med school applicants. And so one of them was quantify and interpret change in dynamical systems, or explain homeostasis in terms of positive and negative feedback. There was also caused by the National Research Council of the National Academy of Sciences, where they say that students, for the report was called Bio 2010, they said that students, for the students, an emphasis should be not on the methods, which is not what we do in math courses, unfortunately, but rather on how the methods can be used to understand, elucidate biology. So and finally, NSF, they talked for a greater emphasis on modeling, computation, and data analysis tools. So the goal was really to use these elements and make that into a first-year math course for the students. Let's just have a look at what was done in the old version of the Calculus for Life Sciences course. What do we have here? And that's already a version that I think, as compared to other Math for Life Sciences courses that I've seen, is already quite closer to biology than other courses. So here we have, so the two columns really are connected to the first and the second quarter of the course. So modeling with functions, okay, that's good. We have some modeling, but it's really real numbers and functions, power functions, exponential growth. And then it's really the more traditional calculus course, limits and derivatives, definitions, limit laws, computing limits, the derivative of the point, then differentiation rules, so very computational. Then we have applications, so graphing functions, optimization, integration, and finally introduction to differential equations. So why there's nothing wrong with that, that structure here? You see it's not directly connected to the goals that were explained just a slide before. And also the other thing is that in this case, as math courses are typically taught by math departments, you can see that with these topics here, it's very easy to completely forget biology and really just focus on the math. Oh, how do we compute the limits? What are the different laws? Let's compute derivatives by hand. And then you spend a lot of time on that, and let's prove the rules. Integration, fundamental theorem of calculus. Okay, let's do that. Integration techniques. Again, nothing wrong with that, but not connected to what is really being necessary for the undergrad students in biology and the life sciences. So what did we do? How did we start from there and then got to a new course? So let's talk about LS30, which is Mathematics for Life Scientists. And that's the new version of the course. Let me talk a little bit about the structure. So right now it's a 2-quarter course. So we're on the quarter system at UCLA. Over the years, so it started in 2013, has become large. So now we have 1,900 students per year. It's really, really large. It's first-year students, the vast majority of them. Lots of pre-medical students. So with all that comes with it, for those of you who teach pre-med. So a big emphasis on grades, but also really tons and tons of pressure on them. Like they really feel that they need the A in every class. Otherwise, they just do. So the course, it's 115 minutes per week, either 2 times 75 minutes or 3 times 50 minutes in large lectures. And then we have some computer labs, 100 minutes per week. These are in much smaller sections of 25 students. And this is given by TAs. And with the TAs, we also have some undergrad learning assistant that help out. Because the coding can be pretty hard, so we use Sage Math, which is a Python. And for the students who have never done any coding before, that's pretty hard. Well, there's definitely a learning curve. Okay, so what do we do in this course? So I'm going to follow a bit the quarter and give the different topics. So we start by talking about building models. So really how to write down equations. At that point in the course, we call them change equations. Really to introduce it as necessary, but not just put lots of jargons when we don't need to. So at the very beginning, we talk about these change equations. So at that point, we say T prime and S prime just represents here the change in T, the number of tuna, and S, the number of shark, and we don't say more. Of course, many students have taken calculus before, so they know it's the derivative. But at that point, it's also a way for the students who have not taken calculus not to feel behind from week one, basically. So here we really focus on how to write them. How do we find these equations for the Lot-Cavalterra model that we call the shark tuna model? Why do we multiply the two variables together? And then, so pretty quickly, we can get to a bit more complex models where we have different species, where we're going to have, for instance, this one here on the right-hand side, we would give these equations to the students and tell them, well, we have 3 species. We have mountain lions that are preying on foxes that prey on mice. Which is which? And so from here, that comes pretty early, like week 2 or 3, where we can have students already, we try to really go higher in the sense of having more conceptual discussions, rather than a traditional course where you would just spend a lot of time seeing how to solve every single type of differential equation from the beginning and lose the big picture very, very quickly. So here on the right-hand side, maybe you can see that, well, in the y prime equation, we have some logistic models, so some population crowding. So we can talk about that with the students. We also have them discuss, okay, how do we identify which is which? How can we tell who is preying on whom? How do we make sense of these terms that are repeating between the equations? And that gives us the connections between the different species. We can also ask them right away about the hypotheses made by the models. So for example, here, well, the X prime equation, has anyone identified which is which?
So X prime is lion.
Yeah.
And Y prime is probably fox, and it's logistical growth there. And Z prime the other way around, because yeah, Y prime is the mice and Z prime is the fox.
Mm-hmm. Exactly. So in here, we would have students work on that and we discuss. And so here we can identify by the terms the xz that is positive in the X prime equation, and then comes again as negative in the Z prime equation that indicates that X is preying on Z. And then the YZ term that is positive in the Z prime equation and negative in the Y prime equation. And so we can see that Z is preying on Y. And then, so we can also talk, so here it's for Y, for the mouse, that we assume logistic growth. Or we can also see, for instance, that in Z, I have this 0.1 Z term at the very beginning of the equation. So that would indicate that the fox is not, the source of subsistence of the fox is not only the mouse, because I have another term as well. Otherwise, I wouldn't have that term. So there's some growth that comes from something else than from the mice. So we can discuss all these kind of things pretty early on in the course. What other models do we talk about? So we have prey models, basic population models. Then pretty quickly, we talk about models that are unfortunately very useful right now, which are SIR models. So SIER models. So if you don't know these models, that's for susceptible, infected, and recovered. So these are epidemiological models. So for the flu, for COVID, for all these kind of diseases. And so here we can see that I think one big difference with the more traditional calculus course is that here we teach some, we study some concepts that are directly connected to our everyday life in some unfortunate way right now. But we can see right away the connection. And so that's really one big difference, which is that in the many courses I've taught before, and I've taught for general scientists, physicists, engineers, even engineers, they just, yeah, math, that's great, but what is this really for? And I must say that in many cases, I didn't have like really good answers. Whereas here, we don't get that question anymore. Here, that's just very clear. That's a really big thing that we see in student comments. And the other aspect that I like to underline in the course is that, well, there's SIER models, they're using research. They're using research that's done today. We're not only studying theorems that were proved 200 years ago, but also we study concepts and models that are used today. So here, that's a paper from 2020 on COVID, on modeling COVID and finding, well, they have a model, they try to see ahead of time how many cases there will be. Of course, the students, they wouldn't be able to read and understand 100% of this article, but still understanding like really the main concepts, the main features, at the end of the course, they can definitely do something like that. So now, first part, we have the students learn how to write down models, how to write the equations. So another question is, how are we going to analyze these? And how are we going to tell them about solving these equations? Because that's what you want. Well, so we talk about time series. So here, that's again the prey question that I had before. And so here what we say is, okay, let's imagine that I have my shark and my tuna, and that I do some shark removal. I'd like to get rid of the shark in the area. And so I kill just as many sharks as I can find. What's going to happen? And so here, what's really interesting is that, and that's really something we try to move away from, is that you'll have lots of different answers. The shark is just going to go down. It will go back to the same patterns before. There will be a rebound. There will be a smaller oscillation. Can go in all way. And something that a message we really want to get to the students, we really want to get across is, well, at that point, we don't know. Because, especially because we're using models, many models that are very concrete. One challenge is that the students, they're going to reason with like common sense explanations. Oh yeah, you know, there are fewer sharks, so they cannot reproduce, so the shark population just remains really low. And so one thing we really underline is, no, we need a mathematical model to know what's going to happen. Without a model, there's no way. All the different options, all the different arguments would make sense. And so we cannot know ahead of time. We need a model to be able to predict what's going to happen in the future. So how do we study that? But we do most of it, not most of it, the vast majority of it graphically. So here we introduce the concept of vector field and trajectory in the state space. This means that I have my two equations, and therefore to any point in the state space, so for any number of tuna and shark in this case, I can associate a vector that we call the change vector that's going to tell us how the population is going to evolve at that point. That's obviously, we use the derivatives to find that. And then we can talk about the concept of trajectory, saying that, well, if I follow the arrows, I just surf on the vector field, I'm going to follow a certain trajectory. And now we have all the concepts we need to truly answer the question we have on the left-hand side. Because from the time series only, we cannot do that. So we really focus on this idea of vector field and trajectory to understand the future evolutions of systems. Now, for the trajectories, what we do is we use Euler's method. And basically, the point of view that's taken is most of the models in biology and the life sciences do not have analytic solutions. So let's not spend weeks and weeks and weeks learning about all the different types of differential equations, of systems, of everything, because anyway, most of them, you won't be able to solve them analytically. So we introduced Euler's method, and as I was discussing just before, then the program we use actually uses an improved method because Euler's itself is not precise enough. But the idea is really to give them, to teach them an example of one numerical method that you can use that's relatively simple to learn and understand, and say, okay, this is how we compute these trajectories. We use Euler's method, and then we can just compute them. And then, okay, we have some other improved methods, but the basic idea is here. So after this first part, general part on introducing modeling, we have a more traditional part, where it is the definition of the derivative, some differentiation rules, but very lightly, linear approximations and integrals. And here, it's going to depend on the different instructors, on how much time and to what level of detail you want to go. Personally, I really focus on the conceptual part, on the definition. And the idea is really that, well, if you want to compute derivatives, we have computers that do that very well, probably better than humans. So we're just going to have students do that. I do have them compute some derivatives by hand because I want them to at least do that a few times, understand the basic mechanics. But the typical problem sets where you have 10 or 20 derivatives to compute by hand, we definitely can do that. So it's really this part, at least for me, is really de-emphasized. Okay, so so I should say two things. First of all, well, we need this more traditional calculus part because we're using differential equations that do use derivatives. So obviously we need to explain what the derivative is at the point. I think another reason is that this is, for the life science students, that replaces the calculus course. Well, that's the new version of the calculus course. And so I guess if you have a calculus course, at some point you need to explain what the derivative is. It's kind of a compulsory part. So one thing we do emphasize is the idea of linear approximations, because then that's going to lead us to linear stability analysis. So that's the part that comes right after the calculus part, which is, okay, now we have seen how to write down equations. For example, here, so if X is a population, we have logistic growth. So growth will population crowding. So how do we know what's going to happen in the long term? And I think that's really one big thing in the course. It's always focusing on long-term behavior of systems. How can we predict the future evolution of the system? And how is it going to change or not? So these are really what we want to focus on. And so here, using linear stability analysis, first of all, we introduced this idea of graphing the equation of the differential equation, if I can put it this way, by graphing x prime versus x, which is really typical to analyze differential equations, and also then be able to determine for the equilibrium points, or the points where the system does not evolve, where the derivative is zero, the type of point we have. So technically the stability of the equilibrium points, to know when I have a one-dimensional system such as this one, whether the system is going to be attracted by the point, such as the one that we have at K, or pushed away from it, namely if it's unstable. So here, that's the point we have at 0. And also the thing is, having taught linear approximations for many years, I was never completely clear on how it was really used, because I knew the really math part, or the perspective from mathematician. Oh, what is a linear approximation? How you compute it? How do you compute the maximum? You're doing these kind of things, but how is it like concretely used? Okay, so now we have this idea of linearizing the system. Being a pure mathematician by training was not something I had studied in courses. So now, what do we do with two-dimensional systems? So here we have a competition model. And again, the idea is, as soon as we can, to use the vector field and the trajectories. So here we have a deer moose competition. So they compete for resources. Again, here we're going to focus quite a bit on, okay, what do the different parts of the equation correspond to? What assumptions are made? The competition between the deer and the moose. So here, X represents the deer and Y represents the moose. On which of the two is the competition the hardest? Do we have competition within the species, interspecies competition? Yes, no, why? So it's really looking at understanding the system as a whole rather than doing lots of computations. By the way, I know I'm not showing any computation here. Our students do some computations, right? I know I'm saying, oh yeah, we do everything graphically. No, we do computation, but definitely less computations by hand than a more traditional calculus course. And so here, to answer this question here, on the right-hand side, so what's going to happen in the long run with these two species, this deer and moose species in this area? Well, let me show you just the trajectories. Now we see that better. And so here, again, that's the same mantra we have for the whole course, which is follow the trajectories. Just go with the flow. And that's going to lead you to the long-term behavior. So here in black, the black dots represent the equilibrium points of the system, so where the system does not evolve. And the one that's at 5, 5, the one in the middle of the quadrant, so here that's what we call the saddle node. So it means that the trajectories, they're going toward it and then moving away from it. And so here, the big question we want to have the students answer is, are we going to have coexistence or not? Are these two species going to coexist or not? In this case, because the trajectories, if we look at them, they either go to the point 15, 0 on the horizontal axis or the 0, 10 on the vertical axis. So it means that in both cases, one of the two species goes extinct. And what's also having this of using the vector field also gives us the opportunity to talk about influencing the system. So before I said, oh, let's do some shock removal and let's see what happens. Here we can have the exact same kind of conversation, which is, oh, if there's a disease that kills some moose, and then the moose population was at 15 and it goes down to 10. Do I have the same long-term behavior, or is the long-term behavior changing? And what I want to say with that is that we really look at qualitative change rather than quantitative change. Of course, we would like to know in the long run how many moose and how many deer we're going to get. But more importantly, we want to see, oh, if I have that system here, what does that need to change in the equations to get a different outcome, to have a qualitative change? So this way we can introduce the idea of bifurcation, where the system is going to change, not just in the numbers of deer and moose, but really in going from coexistence to non-coexistence. So in terms of bifurcations, I didn't know which example to pick. So I took the one that I personally prefer, which is the spruce birdworm model that we study. The idea is the following. So we have these birdworms, these little worms that we see on the left-hand side, and that inhabits forests pretty much all over North America now, and can completely defoliate and kill a forest. And so it's something really important for forest conservation to manage that properly. So from the equations that we have, so the first part, the Rx times 1 minus x over k, that's the logistic growth for the worms. And then on the right-hand side, I have predation by birds. I'm going to go into the details here why this equation, the x squared over 1 plus x squared, maybe you can recognize a Holling function here. So that's the typical saturating functions. So how do we analyze that? How do we know what's going to happen in the long run? Well, when we look at equilibrium points, so I rewrite my equation, factor x out. Now I have the part in red, r times 1 minus x over k. That's giving me this red line that's going down. And I have minus x over 1 plus x squared that gives me the curve. When we look at that, where the curve and the line intersect, that gives us the equilibrium points of the system. And then using here a graphical method that we can call the over-under method, I can determine the direction of the vector field. So I can determine whether my equilibrium points are going to be stable, namely attracting the system, or unstable, namely pushing away the system. So in this case here, we have one parameter, which is R, which is the growth rate of the birdworm. And if I take R being equal to 0.4, then I have this bistable situation. I have one stable equilibrium point with a small value of x, one stable equilibrium point with a high value of x, and an unstable one in the middle. So far, so good. So now the question is, what happens if R varies? If this growth rate for the birdworms goes up or goes down, what is going to happen? And so here, the number of equilibrium points is going to change. The number and nature of equilibrium points is going to change. And we're going to get different outcomes. So what are they? Okay, so now that I'm talking, I'm realizing that I'm definitely skipping a step here, but I have a bistable region. But let me try to mind the gap here. So in the middle region, on the left-hand side, I have my bifurcation diagram. On the horizontal axis, I have K, which is the carrying capacity, or not the maximal, but the ideal number of budworms in the logistic model, and R is the growth rate. The situation that I have on the right-hand side here, that's a typical bistable situation because I have two stable equilibrium points and one unstable in the middle. Now, I'd like to have something that I can move. If R is increasing, what's going to happen is that my red line, let's say I just change R and I keep K constant, what's going to happen is that my red line is going to become steeper and steeper, like that. And therefore, instead of crossing the blue curve 3 times, as it does on my diagram here, it's going to cross it only once. And it's going to cross it on the right-hand side where the X value is high. And so when I have something like that, I only have one stable equilibrium point with a very high value of X. So this is what we call an outbreak. An outbreak is when you have lots and lots of budworms. And here you have just one stable equilibrium point and lots of budworms. That's an outbreak. Then the situation I have here is bistable. I can have either a low or a high number of budworms. And if, on the contrary, I reduce R becomes smaller, then the line is going to become flatter and flatter. And again, at some point, is going to cross the blue curve only once. But now, the point where it crosses, I have a really low X value. It's going to be on the left-hand side. And again, it's going to be stable. And so this is a situation that's called refuge. Refuge just means that there's one small number of budworms, and that's stable. So we're going back to that point.
Steve, can I ask you a question?
Of course.
So I'm a little confused about the diagram on the right. That's for a given R value of 0.4. And the blue curve, of course, is R and K independent. So but you've shown a few different K values, which is what's confusing me because yeah.
I see. No, okay. That's a good point. It's good you asked because actually that's something that is missing. So here I'm just taking, I'm just looking at K is equal to 20. Okay. So I just set at the start K is equal to 20 and I only have R varying.
All right.
And then, but that's right. Then you would do the same thing, the same computations for another value of K, etc. Okay. Yes, you're completely right.
And then you construct the phase diagram. Okay, I understand now.
Yes. And so why did I show this one? Well, because that's one of the bifurcations that I like the most because, so here the diagram, the bifurcation diagram, the left-hand side, it's 2-dimensional. And so we have a construction on the right-hand side. So what we tell the students is, how do we determine these different regions in the bifurcation diagram is, well, you're going to do some simulation. You try lots of values of K's and R, you write your code in Python, you try it, and you determine that. That's one way of doing it, to determine when you switch from an outbreak to a bistable region or from the bistable to refuge. But actually, behind that, you can compute analytically what the equations of the black curves that separate the different regions are. And so I really like it because there's some very concrete example at the start, some interesting math that's accessible to students, and also some more advanced math that we keep hidden, but that's here. And that's also something that I want to mention, which is that many times when you have a calculus for a life science course, it's just the watered down version. It's the dumbed down version of the calculus. It's not the real calculus. And unfortunately, that's how some faculty see it, how some students see it too. Well, students, they see more as, oh, that's the easy version, so I'm going to take that one. It's going to be an easy A. But here we teach, like, there's some real content, there's some real advanced math. Of course, we're going to teach an introduction to that, but it's really not, oh, let's dumb thing down because these students, they're not good enough anyway. It's really, no, it's okay, we're going to teach some real interesting dynamical system content, and here bifurcation theory, but accessible to first-year students. Okay, so I see I'm talking a lot. Let's see. Okay. Oh yeah, I think I can just continue. Should be good. So I was talking about bifurcations. Then the next part, we talk about our oscillations and half bifurcations. So then that's one of the parts that I really like in the course. So when the system goes from oscillations to non-oscillations, when it starts to oscillate. So here we take the model of the hypothalamic pituitary gonadal hormone oscillations. So we have these three different hormones taken all together, they form a negative feedback cycle. And we have a model that's given here. It has normally more constants, but here I have just set some of them to make it simpler. And so if we solve this model here, what do we get? Well, let's solve it first. So here I have the different hormones, the gonad, hypothalamus, and pituitary hormones. And we see that I have some oscillations and then it stops oscillating. Okay. But, and that's where that becomes really interesting. What you can notice here is that in the H prime equation, the first equation, I have 1 over 1 plus G to the power n. So what is the value of n? So here, what I've not said is that to do this simulation here, I took a value of n of 5. So now what happens if I change this value and let's say put it equal to 9? Well, now I get to stable oscillations. And so here, what we have is actually a half bifurcation. That means that we have switched from stable equilibrium to stable oscillations. And here, if we look at that in the state space, so in the three-dimensional space, what do we see? So here, it looks flat. It's actually three-dimensional. But so the important part is the red oval we have in the middle. And we see that the green and the yellow trajectory, they spiral either inward or outward toward this red oval. And that's the stable limit cycle. And so we can discuss with the students, oh, how do we get there? A half bifurcation is actually a creation of one of this cycle based on the values of the different constants that we have in the model. Okay, yeah, time is running, so let me then just quickly, for the last part of the course, we talk about chaos. So here we have what we call a strange attractor. So how we talk about chaotic behavior and how it's not what students usually think it is to have chaos. Linear discrete time systems, and then partial derivative, and we go back to half bifurcations again. Okay, so the outcomes. What has happened now that I have shown you quite extensively what we did in the course? What are the outcomes of this course? What has changed? Well, if we look at the perception of S30, it's been very, very positive. So the one I think is the most interesting is the one on the right-hand side. So these are a survey that was given in 2014, 2015 to students who had completed S30. And we see that we have over 90% who say that I saw the real life application or relevance of what I learned, which is typically something that's just really hard. The other thing is I look forward to taking more courses in the life sciences. And let me tell you, it's not small. It's not a small feat for a math course to encourage people to take more life science courses, right? Well, yeah, life science courses. So not even math courses, something else. And I hope it's not, oh, I hate this course, so I'm looking forward to taking something else. And the other thing, and that's something that was really very different in the old course, and also a result that's known generally, which is that for math, for calculus courses, but it's also true for physics. Most of the time, when students take their first college course, math or physics course, their confidence in their math or physics ability or chemistry ability usually goes down. And here we have nearly 80% saying that the course helped them increase their confidence in their math ability. And that's something that we hear quite a lot because the students come with what I would say this trauma from high school, or even those, or especially those who have taken AP, which is all these rules to learn these computations to be done by hand. And here we do something different. We look at concepts, we look at graphs, vector fields, how to interpret the data instead of focusing on the process. Now, when that started, this course, there was one concern about students, and mainly that they wouldn't have the background necessary to then take the chemistry and physics course that they typically take after the math course. And so that's something that was studied. And so they looked at physics 6A, which is the first physics course that students take after having taken S30. So math 3 is the traditional calculus course, and that's from the years where S30 was really small. And so the two courses were running in parallel. That's still the case, but now S30 is really, really big and math 3 is very small. And so we see that actually students who had taken S30 perform better than students who had taken math 3. So this prediction that we were going to doom the students and that they would just do super poorly in other courses did not happen. And if we look also at URM students, that was another concern. So here, that's the grades in physics 6A just for URM versus non-URM students. And so we see that in terms of the mean or the percentage of URM students who get an A or A plus, well, we have nearly double compared to those who took math 3. And also for A minus and B, the percentage is much higher. And now one may think, well, I look that you have very few URM students who took S30 and many who took math 3. So maybe you're comparing apples and oranges. And so your statistics here do not hold. Well, even if you do some, so we did some propensity score matching to make sure that we had comparable populations. And even after doing that, actually the difference between the two groups increased in terms of the mean for the URM students. So one last thing. As I mentioned before, before I came to UCLA, I was at Cornell, and we did completely over there redesign the math for the calculus for life science students. And that was slightly different in the sense that here at UCLA, the Division of Life Sciences decided to create a new course. So they started from a blank slate. At Cornell, we had an existing course, and we decided to redesign the course. So now the course follows, uses the same textbook and follows generally the same structure. One big difference is that the course at Cornell, we don't have the computer labs. There were several reasons for that, but having the computer labs really increases a lot of the complexity of the teaching. And also the other thing is that at Cornell, it's really taught by the math department. It's not taught by some biology or life science department. So, well, the good news is that it is possible to have math department teach that course. It does require some learning, and maybe that's one of the challenge, which is that if you have just a very traditional calculus course, you can take any faculty, any grad student, and have them teach that because they have done that before and they expect to be able to do it. For this course, well, you need to learn, I had to learn some of the biology. I had to learn dynamical system. That was not my field, so I had never learned that before. And so it's not as easy to staff to find the right person to teach that. Whereas traditional calculus is no-brainer. You just give it to basically anyone, and they're expected to do an appropriate job. And the other thing that was, and I conclude on that, the other thing that was surprising at Cornell was, since we're taking an existing course and redesigning it, what I did not expect was the difficulty of going against the inertia, in the sense that students would think, oh yeah, that's the easy math course. And then when we changed it, and we told the students, that's not the same course, it's different, it's not what your friends told you last year and the year before, and etc. But still, they wanted that easy math course that they had been promised. It was also hard. It was not hard, but the thing we did not realize is how to get the word around campus also with other departments, with faculty, students, advisors. We had even advisors saying, oh yeah, that's the easy course, take that, you don't need to work a lot and you get your credits. And then students got into trouble because they didn't know about that. So getting the word around that, no, that we have completely redesigned the course. Now it's different. But that was also good to have some faculty, biology departments saying, thank you, we've been asking for that for many years now, you're doing it. But that was really a surprise challenge for me. Okay, my time is up. So thanks a lot for your attention.
Thank you, Steve. Very interesting talk. Questions from the audience? Just unmute and ask. No. Anyone? If not, while we are waiting for others to, maybe I can ask a couple of questions. So, how did you decide on the assessments in this class? So what kind of homework you gave, what kind of exams you gave, so as to give them the opportunity to both understand what they were doing and also try this out numerically?
So I would say, so we have homework and we have computer labs. The homework is going to focus more on the conceptual part and also doing some don't want to say easy, but a few computations by hand to really see the mechanisms and have them do things by hand a few times. And then the computer labs is going to have them code the methods. So for example, Euler's method is a good example. We will have some homework where they have to do Euler's method, but in the homework, we're going to ask them for 2 or 3 steps. There's no point of doing 20 steps by hand. But we're going to ask them about what's the influence of the time step on the method, these kind of things. And then we will have a computer lab where they code Euler's method, and then they can compute 10,000 steps, or well, just as many as you want. So in general, the idea is homework by hand is going to understand the concept, understand the basic mechanisms, doing a few computations to understand how things work and the different concepts. And then we have the computer labs for, I would say, the true computations.
And are there exams for the class? Or?
Yeah. Have you ever seen a class without exams? Yeah. So here it depends on the instructors. Some instructors, they focus really more, and also I should say, so the instructors, we have some instructors who are mathematicians by training, others who are biologists by training. And so there's sort of a spectrum of emphasis, what people put emphasis on, and even within, so I'm in the math group, but I focus definitely less on computations by hand than some of my colleagues that put more emphasis on this. So in terms of exams, I should say that we really focus more on the conceptual part and doing a few computations by hand. It really depends. Some of us include a bit of coding in the exams, others don't. So here there's really a variety. It really varies quite a bit.
Other questions? My computer is making a noise. So the course at Cornell is continuing?
Yes.
Yeah. And so you're continuing to gather statistics. So I presume you'll have larger n values to compare gains as time goes on. Is that correct?
Well, we had to start again because the person who was doing that then left UCLA. So and no one has picked up that part. So we need to work on that. But we definitely want to work on equity gaps within the course and see how to reduce it.
And if you had to, I mean, do you feel that this range of topics that you have currently got in the course covers the things that life sciences students need, or is there something that's on your wish list to, that you would like to have included?
Well, I'm not sure I'm the best person to answer that. On my end, I feel we do a good job in terms of what is useful for the students and what we can reasonably do in 2 quarters. But I think it would be more biology faculty that you should ask on whether we do all they need or not. What I would say is that right now, one desire we have would be to have like a next course, a higher division course, because now we have students who follow these 2 quarters, they're very motivated, but there's nothing coming up next. Well, there's a stats course, but there's no course or students can do projects on the models that we study. So what I would like to do is to have something slightly more advanced that the students could take after taking this 2 quarter sequence.
presumably you could also have things like little projects that they do based on these models.
Yeah. Yes, definitely. Yeah,
Yeah,
that's
very-
definitely something I'd like to develop over the years.
yeah, this is really fascinating. Um, any other questions, anybody? Well, thank you so much for this, Steve. This was really very, very, very interesting to hear, and I hope we can put similar things into practice here.
You're very welcome. Thank you for the invitation.
And I see that there are some materials available on the web for people who might be interested. Is that correct?
Yeah, definitely. There's a website that comes with the book. So first of all, you probably have access to the textbook because most libraries, it's edited by Springer. And so most libraries have an agreement with Springer where
Okay.
you can just get it free. And always, I've just posted in the chat the website that comes with the course. And if you want some more teaching materials, slides, homework sets, these kind of things, then you can email Alan or myself, and then we can share some more materials.
Okay. Wonderful. So thank you again, Steve. Thank you for taking time to speak to us.
You're very welcome.
Yes, Steve, is very good. Thank you.